So, for today, I need your attention up here, please. We are still working through evaluating definite integrals, actually, today is more just a focus on definite integrals, not indefinite integrals, but actually having limits of integration. And then also applying integrals, so being able to interpret when you see an integral what it actually means. We have interpreted one context already with the distance problem, that if you have or are given velocity and you have the integral of velocity, that's calculating the distance or the displacement if the velocity isn't always positive. But this is just applying it to more context, not just the physics context. So we have here the evaluation theorem. This we talked about Thursday. So if you were gone, you haven't caught up with that yet. By the evaluation theorem, if f is a continuous function on the closed interval from a to b, then to find the integral from a to b of f of x dx, you find the antiderivative of f, which would be, I'm going to write this another way, which would be capital F of x, the antiderivative, and you evaluate it from a to b. So that's what capital F of b minus capital F of a represents, the antiderivative evaluated from a to b. This is now just writing it a different way. So if capital F is the antiderivative of little f, this means that little f is really equal to the derivative of capital F. So we could rewrite this equation like this. So all they're doing is they're replacing little f of x with capital F prime of x. So if you take, basically what this is saying is if you take the integral of a derivative, you're just getting back to the original function because you're taking the antiderivative. But it's also showing then that the integral of a rate of change is equal to just the total change of whatever context you're working in. So it says capital F prime of x represents the rate of change of y equals capital F of x with respect to x. Capital F of b minus F of a is the change in y when x changes from a to b. So they're reformulating that evaluation theorem and they're calling it the total change theorem. So saying the integral of a rate of change is the total change. So capital F prime is a rate of change. When you integrate that, you're getting the total change. So these two examples are just interpreting. We're not actually finding an integral. We're just interpreting what it would mean in context. When you interpret, you need to take into consideration both the function and the limits of integration. So you need to interpret or include both when you interpret. So example 1 says the current in a wire is defined as the derivative of the charge. So let's see here. So I of t, this would be the current Q of t. So it's showing that current is Q prime. It's the derivative of charge. So Q of t represents charge. And then it's asking us, what does the integral from a to b of I of t dt represent? So if you were to find that integral, what would the meaning of it be? Yes, so I could rewrite this. The integral from a to b of I of t dt would really be the integral from a to b of I of t is equal to q prime of t. And therefore the integral of this would be just q of b minus q of a. This? You would not, no. I'm just writing that out. So actually writing out in words what this meaning is then. The Q of B minus Q of A is if Q represents charge, this would represent the change or the total change in the charge on that interval. And we have just a general interval here. So I'm going to say the integral from A to B of I of t dt represents the total change in charge on the interval from A to B. So on free response questions, if they're asking you for a justification or an interpretation, I'll be honest, I don't know for sure if it's something they take off for, but I know on all of the answer keys, a justification or an interpretation should be a complete sentence. So try to write those as a complete sentence. Usually it's just one sentence, but write it more formal than maybe you would just on your own practice. Okay, questions on that? Just interpreting what it would mean. Okay, so if we look at example 2, I included a second one. It's a different context, but it also actually includes values for A to B. This one says the marginal revenue function, which is R prime of X, is defined to be the derivative of the revenue function, R of X, where X is the number of units sold. And it wants to know what the integral from 1,000 to 5,000 of R prime of X dx represents. Any ideas on how you would phrase what this represents? Represents, I would say, I would just add the total change in revenue. And then because we know X, it's specifying X is the number of units sold, we could say on the interval from 1,000 to 5,000. But I could say the total change in revenue from 1,000 to 5,000 units sold. Just because I know, or it's specifying X is the number of units sold, so on the interval from 1,000 to 5,000 would probably be fine. As long as you're taking the interval into consideration and not just saying it's the total change in revenue. Okay, so always think when you're interpreting these, when you find the integral, the interpretation is you're finding the antiderivative. So what is the antiderivative of the expression you're taking the integral of? That's what you want to think of. Any questions on those two? Okay. The last example, I just have, well, example 3, I shouldn't say the last one, then we'll actually go through a specific problem. But I need your attention up here, please. This example, it's writing it out, I don't know, more formally, I guess. But it's the physics example that is the most common, comes up the most often. So if S of t represents the position, displacement of an object moving along a straight line at time t, then what is S prime of t? velocity, v of t. So that represents the velocity at time t. So therefore, if you have the integral from on a time interval t sub 1 to t sub 2 of s prime of t, that means you're taking the integral of velocity. This would then equal the position or displacement evaluated at t sub 2 minus the position evaluated at t sub 1. And that would represent, don't say it represents distance. It only represents distance if on this interval velocity is known to be positive the entire interval. So it represents the change in position or displacement. On the time interval t1 or t sub 1 to t sub 2. And we're going to talk about distance below. So it's only distance if the velocity is known to be positive, because then between that curve and the x-axis you would have a positive area. That would be the distance traveled. So if you want to calculate distance, you have to consider intervals when the velocity is greater than or equal to 0. So if the particle is moving along a straight line, it did specify that above. This means it would be moving to the right. And also the intervals when the velocity is less than or equal to 0, meaning the particle would be moving to the left. In both cases, distance is computed by integrating the absolute value of velocity or integrating the speed. Okay, so if you just take the integral of velocity, you are finding displacement. If you take the integral of the absolute value of velocity or the integral of speed, then you are finding the total distance. So what you're doing is, and it kind of shows on this diagram to the right. So say this is your velocity curve from t sub 1 to t sub 2. This area that's below the x-axis would be subtracted. Your integral is giving you net area. So that would give you the displacement. Here it's moving forward, then back, then forward again. But if you integrate the absolute value of velocity, now you're taking this area and it's also being added to a sub 1 and a sub 3 to get the full distance traveled. So you're thinking of any area that's below the x-axis as actually being positive, meaning you need to know on what intervals are you actually below the x-axis. We're going to go through an example where we actually do find displacement and distance. But then I have here too, integral of acceleration would be what? Velocity. So this would be velocity evaluated from t1 to t2, so velocity of t sub 2 minus velocity of t sub 1, or the change in velocity. Okay, so as you work through, as we work through this example, I have a worksheet for the practice for this section. Always be thinking if you're finding an antiderivative, what integral are you setting up? How could you use an integral to answer your question? So we have a particle moves along a line so that its velocity at time t is the v of t function here, measured in meters per second. In part A, we are finding the displacement of the particle during the time period 1 to 4. So if I'm finding displacement, all I'm doing is finding the integral of velocity. So integral from 1 to 4 of v of t dt, which I could write out as the integral from 1 to 4 of the quantity t squared minus t minus 6 dt. For distance traveled, you do. So displacement, you do not need it. Distance traveled, you do. Okay, so I did show on Thursday, we first looked at how to evaluate integrals by hand. You might use a calculator to get the values you need. but then I also showed on the calculator, you have to know both ways. Okay, so how would I find this integral without just punching it into my calculator? Dalton. Yes, but I don't have S, I have V. Find the antiderivative, yes. So you find the antiderivative and then you evaluate it from 1 to 4. Okay, so what is the antiderivative of...
1/3 T.
Okay, and then minus antiderivative of T minus antiderivative of 6. You don't need, so yes, but you don't need a plus C when you have the limits. So we don't need a plus C, we're just evaluating this from 1 to 4. Okay, now this part, can you use your calculator for this? Yes, but realize, usually if you're not, that's very nice, but you have to know how to do it without a calculator. So realize if you were actually doing it this way, you probably wouldn't have the calculator to plug these values in, but for right now you can. Still good to know how to do it. Yep. All right, so I'm going to show you this on your calculator again. I know I've showed you this before. If I type in this function, so 1/3 t to the third minus 1/2, I'm just going to put 0.5 t squared minus 6t. I know I'm using x's, not t's. I know a lot of you go to the second graph, you go to the table and type in the values, but that's just going to give you decimals, and if you can recognize, oh, this decimal is this fraction, you'd still be able to give your answer as a fraction. I think I've showed you this before. I'm going to show you another way that you can get a function value doing the vars. So I have this typed in to y1. I'm just going to do second quit to go back to my home screen. So if you hit the vars key, which is next to clear, and then you go over to yvars, you are dealing with functions, so just hit enter for number 1, and then you pick which one you typed it into. So I entered it into y1, so I hit enter. So this is now, I then put in parentheses, I want to evaluate this when my value is 4. So it's like you're typing in f of 4 into your calculator, and then you hit enter and it gives you that value. But what's nice then is, okay, I get this. I know that's negative 10 2/3, but right from here I can do the math, enter to change it to a fraction right away. So I like to do that this way. I like to leave my answers as exact, have them as fractions. So just reminding you of that too, there's different ways to get those values. So when I type in 4, I get negative 32/3. And then if I do that again, I could actually, well, I'll show it again. So vars, go over to yvars, enter for function, enter for y1. Now I'm evaluating it at 1. Enter. If you don't recognize what fraction that is, if you have a repeating decimal, it is a fraction. I can change it to a fraction. It's negative 37/6. So I have negative 32/3 and then minus negative 37/6. So negative 32 divided by 3 minus negative 37 divided by 6, enter negative 4.5. And even though this is a decimal, this is exact. If I rounded either of these, you would not get negative 4.5 exactly. So that's why I'm showing you this, to help you get the exact answer. So this is the displacement. You did not get negative 4.5?
I got 5.
I'll remind you again, because I know some of you were gone, how to get this value just by typing the integral in your calculator. But I also want to ask you to interpret this. It says find the displacement, so it's negative 4.5, but what does that actually mean? Yeah, so at time, or from 1 to 4, the displacement is 4.5, what are we in, meters? To the left of the starting point is what that negative 4.5 would mean, just so you know what that means. But then if you were gone, there's a couple ways to do this. This is the way I showed. You don't have to graph anything to evaluate an integral on your calculator. So just as a reminder, you can go to Math, and then option 9, FNInt, FNINT. And if you have an 84 plus, you probably get this very nice screen. You just type in your limits of integration, your function, your variable. So from 1 to 4, the integral of x squared minus x minus 6 dx is negative 4.5. So, calculator questions on the AP test. Do this. They will often give you integrals you cannot find an antiderivative for to force you to use your calculator, or that way they know if you don't know how to use it. So you have to know both ways. There will be no calculator and calculator questions, like most things in this class. That's why there's 2 parts. Okay. Now, distance traveled. No. It is the integral from 1 to 4 of the absolute value of velocity. You're integrating speed. What this means, I'll show you how to type in with the absolute value in your calculator too, but I want you to see the meaning of it. If I graph, I'm going to graph my velocity function. I still have it typed in as y1. So I'm going to graph this on the interval from 1 to 4. Maybe oh no, I didn't type that in correctly. I lied to you, I'm sorry. I had the antiderivative typed in. Hold on. I need the velocity typed in. Okay, trying again. This is the correct graph I was trying to graph. I'm graphing the velocity. So as you can see, and this is why your displacement was negative, there is more area between the curve and the x-axis. There's more area below than there is above the x-axis. So this does actually intersect the x-axis at 3. You could check that on your calculator by finding the 0, but it is actually at 3. So what this means is the area that's below, I'm going to set this up as 2 integrals. I have to find the integral from 1 to 3 of the velocity. But because I know this integral is negative, I need to take the opposite of it to make it positive. And then I add to that the integral from 3 to 4. And that integral, that area is already positive, so I just leave it as positive. Okay, so that's what you're evaluating. So I'd have the opposite of the integral from 1 to 3 of, just writing my velocity function out, plus integral from 3 to 4. And then the nice thing is both of these have the same antiderivative. It's just a matter of how you're evaluating it. So I have the opposite of the antiderivative was 1/3 t cubed minus 1/2 t squared minus 6t, evaluated from 1 to 3. So I would evaluate that and then apply the negative, plus that same antiderivative, evaluated from 3 to 4. Okay, and I'll actually show you this too. So I have the opposite of. So what I showed you before, because I still have, go back to my home screen, I still have my antiderivative typed into y1. So I'm going to do the vars thing again. So I go to vars, y vars. I can do this as well. Function y1. I can evaluate that at 3. And then in the same step, before I did it separately, I could do minus vars, y vars, y1. Or wait, did I do that right? Yeah, I did. At 1. So I could do that all in one step and get that value. I'm going to change that to a fraction. That's negative 22/3. So I'm taking the opposite of negative 22/3. So it's really positive 22/3. And I'm adding to it. Now I have to do that same thing from 4 to 3. So I'm going to go back up here. If you have an 83, I know you can't do this, but... Yep. But I'll show you how to type this one in your calculator too. There's a more efficient way than this. Yeah. So from 3 to 4, that area is 17/6. So then I'm really adding, I have a positive 22/3 plus 17/6. And that is 10 1/6, so 61/6 would be the exact. This is 10 1/6, and that would be meters. So the total distance traveled is 61/6, or 10 1/6 meters. Now, how to type that in without typing in, I mean, I know I use the calculator, but rather than typing all of this in, you can, if you, I don't know if I've showed you, you can type in absolute value in your calculator. So I'll move this just in a moment here. So if I go to math, option 9, for my integral, so from 1 to 4, for my expression, I want to type in the absolute value of velocity. So absolute value is under the math key, and if you go over to the NUM, the very first option, ABS, is absolute value. And if, again, you have this calculator, the absolute value bars actually come up. 83s, it'll just stay ABS, and you have to put it in parentheses. And then I would type in the x squared minus x minus 6 in the absolute value, dx. And I should get 10 1/6. I don't know if this will change, no. I don't know why that 5 is, or the 853. I don't know why that's that way. Yeah, I don't know why I did that. But if you're doing it this way, it's probably a calculator part of the question, and if you, so then if you have it rounded to 3 decimal places, that's what they're looking for anyway. So that's how you type in absolute value. Yes, Dylan? No. Nope, because you have your limits of integration, that takes care of the interval for you. Yeah, so if you have an 83 and you have trouble typing stuff in, please let me know, because I know that's more complicated. Okay, so I have